Okay, we're going to start having a look at the first application of integration, something you can use integration for. And it's called the area under a curve. And here's a curve I prepared earlier. It's a nice friendly one you've probably seen before, the old well-known parabola. So just simply y equals x squared. And the question that we want to be able to ask is, let's say this is the point 2, is I want to know what this area is. Okay, this has a few engineering uses. You can imagine if you can make that spin around the axis, you can make a bowl, and you might want to know what the volume of the material in the bowl is. If you're making a casting, you'd want to figure out what that was, and you need to know that area to be able to work out the volume. It also has uses in kinematics. If you've got a velocity time graph, then the area under it is the distance travelled. And there's quite a few applications that you'll come across as you go on where knowing the area under a curve is very useful. Okay, so how do we figure out that area under the curve? Well, the first thing is we need some notation to describe it. And given that I'm giving it in the integration section, it probably shouldn't surprise you too much that the notation includes an integral. So the area is equal to the integral of x squared dx. Okay, so when you integrate something, you get the area. The only problem is that how do I know that's that area I'm dealing with and not the area between here and here? I mean, I haven't anywhere on this thing told it what the particular bit I'm integrating is. So what we do is we put the 0 and the 2 on the integration sign. Yep. So these are called the limits of integration. So we'd say the integral between 0 and 2 of x squared dx is the language that you would use for that. But it's kind of nice. It's got the function in it. It's got the things I'm going between. It's got everything I need to know I'm talking about this particular area under that curve. Okay, and then we just do the integration, and then we worry about the limits. So the first thing we do is we integrate x squared, which according to integration things is 1/3 of x cubed. And I drop the integration sign because I've done the integration. I don't need to leave that in there anymore. But I haven't dealt with the 0 and the 2 yet. So what we do is we just put some square brackets around it, and we put the 0 and the 2 on the square brackets. Notice also I've dropped the plus c. This is called definite integration, and once you start plugging the numbers in, you don't need to worry about the plus c anymore because you've got the actual definite curve, and you're not worried about whether it's got a constant added onto it or not. So we're good to go without worrying about the constant. Okay, so what am I going to do with these 2 and the 0? And the answer is you plug the 2 into the equation, so 1/3 2 cubed, minus the bottom one plugged in, 1/3 0 cubed. And then you reach for your calculator and you get 8/3 minus 0. It was easy, 0 cubed is 0 times 1/3 is still 0, so minus 0 makes no difference, so just 8/3. So the area under here is 8/3, whatever your units are, squared. Okay, so if you're measuring this in millimetres, it would be 8/3 square millimetres, just under 3 square millimetres in this piece here. Okay. If you think about it, that doesn't seem unreasonable, because that would be y equals x squared, that's 4, so that whole rectangle is 8. 2 by 4 is 8, and this shape looks to be about 1/3 of that area. Looks about right. So it feels good, and it's come out reasonably. Okay, so that's all you need to do to find the area under a curve, is you need to integrate between the limits like this. So let's do one other one. Let's say we're looking at a cosine curve. So y equals cos x from 0 to pi over 2. Radians, radians, radians. Notice we're working in radians. We're always going to be in radians whenever we do any of these sort of things. And we're trying to find this area under here. Yes. So the same thing is area equals integral 0 to pi over 2 cosine x dx. So we have to do our integrations. If we integrate a cosine, we get a negative sign. So integrating cosine gives us a positive sign. From 0 to pi over 2. So we put in the pi over 2 minus putting in the 0. Sine of pi over 2 is 1. Sine of 0 is 0. So the whole thing equals 1. So that area under there is exactly equal to 1 for a cosine curve. Okay. Notice for both of them, the bottom has been defined by the x-axis. So this idea gives you the area under the curve above the x-axis. The area under the curve above the x-axis. Okay. Let's do a slightly cheeky one and see what we come up with. So if we do something like, let's go for y equals x squared minus 4. Okay, so this point here would be negative 4, which means this cutoff point here is 2. And we're going to try and find this area here. What's going to happen? So again, we're going from 0 to 2, and we're trying to find this area under here. So the area should be the integral from 0 to 2 of x squared minus 4 dx. So we do the integration. 1/3 x cubed minus 4x from 0 to 2. We stick the 2 in, so we get 1/3 2 cubed minus 4 lots of 2 minus sticking the 0 in. 1/3 0 cubed minus 4 lots of 0. What's that? 8 over 3 minus 8, and that lot's all 0, so it doesn't matter. So what's that? That's going to be 24 over 3, so 8 minus 24 is negative 16 over 3. So apparently, this area is negative 16 over 3. And the negative means it's below the axis. So any areas which are below the axis, when you do this integration, will come out to be negative. Okay, definitely something that you need to take into account. And it means that if you do a situation like the cosine one, if we carried the cosine one on to pi, so I let the cosine one go on to pi, and I'd found the area from the start through to pi, so now I'm making this, instead of pi over 2, I'm making it pi. So instead of pi over 2, I've got pi. Instead of pi over 2, I've got pi. And sine of pi is 0, minus sine of 0 is also 0. The answer is 0. So all of this area here is 0. Because this piece is positive and this piece is negative, and they're exactly the same size, and they cancel out. So the total area here is 0, speaking in terms of integration. Obviously, if you decide how much paint you needed to paint this or something, you need more than 0. There's actually stuff there. So in that case, you'd need to work it out up to that point, work out that shows the area, and then work it out to this point and add the two together. Because the integration will think of anything below the axis as negative. Definitely an issue. So if you're trying to do ones where you've got split bits, some above and some below, you need to think very carefully about what your integration is delivering. Okay, so area under a curve, integration is the tool. You need to know what your limits are. Pop them on your integral. 2 steps. Do the integration, keeping the limits the same. Don't worry about the limits while you do the integration. And then evaluate the limits. Top one in first, minus bottom one in answer. Okay? Integration to give you the area under a curve.